In this video, we will practice on another example of using the method of separation of variables to solve partial differential equations. Recall that the foundational assumption of this approach is to assume the solution is of a product type, say u of x comma y equal to capital X times capital Y. Under our assumption, the left-hand side of our equation is simply capital X double prime times capital Y, and the right-hand side of this equation is just capital X times capital Y double prime. Dividing both sides by capital X, capital Y, we end up with capital X double prime over capital X equal to capital Y double prime over capital Y. Since the left-hand side is independent of the variable y, and the right-hand side is independent of the variable x, the outcome should be, in fact, a constant. For the sake of convenience, we're going to denote this constant as the square of the constant alpha. As a result, we end up with a system of two ordinary differential equations, each of which depends on one of those two independent variables. The second step is to solve this system of ordinary differential equations. We have to consider a few different cases in accordance to the value of alpha squared. The first case is alpha squared equal to 0. In this case, the system of the ordinary differential equations is simply capital X double prime equal to 0 and capital Y double prime equal to 0 as well. By integrating those two functions with respect to the corresponding variables, not once but twice, we end up with the conclusion that capital X is equals to C sub 1 X plus C sub 2, and capital Y is equal to C sub 3 Y plus C sub 4. Consequently, the final solution in this case is just a polynomial in X and Y. Since the arbitrary constant could be combined together, so we could slightly simplify the expression of this solution as just capital A times xy plus capital B times x plus capital C times y plus capital D. The second case is to assume alpha squared greater than 0. In this case, the auxiliary equations of these two linear ordinary differential equations with constant coefficients are simply given by r squared minus alpha squared equals 0 and s squared minus alpha squared equal 0 respectively. Solving these two polynomial equations, we conclude that r is equals to plus and minus alpha, and s is also equal to plus and minus alpha. And capital X and Y are equal to these sums of exponential functions with arbitrary coefficients. Thus, the final solution is the following sum of exponential functions. And you can also combine the arbitrary constants to get a slightly more concise expression. The third case is alpha squared less than 0. Note that in this case, alpha must be a purely imaginary number, and we could express alpha as plus or minus of the absolute value of alpha times the imaginary number I. Following the same procedure as in the last case, we conclude that the root of the auxiliary equations are simply given by r equal to positive or negative absolute value alpha I, and s equal to plus and minus absolute value alpha times I. Under this assumption, we could formulate the solution of capital X and Y as the combinations of these trig functions. Hence, the final solution in this case is the following sum of the product of trig functions with arbitrary coefficients. That's how we find some solutions of a partial differential equations with the method of separation of variables. As we have always suggested, if you have time in an exam, it does no harm to double check or even triple check your answers. An exercise left to you is to verify the functions that we obtained are solutions of the given differential equations. So good luck studying math and taking the exam. Thank you for watching. See you next time.